Imagine 1 gram of fuel, smaller than a sugar cube, producing the same energy as 11 metric tons of coal. That's the theoretical promise of fusion. The real question is, how do you actually engineer that into reality? In 2022, for the first time in history, humanity achieved fusion ignition. Not in a sci-fi novel, but in a lab, on Earth. Since then, something's shifted. Fusion has actually moved from theoretical to inevitable, but we're still left with the hardest part, which is turning ignition into infrastructure. One of the most promising tools to get us there, Xcimer lasers. Ultraviolet gas lasers capable of delivering incredibly powerful, precisely shaped pulses of energy. Back in the 1980s, they were the Pentagon's moonshot, the cornerstone of the Star Wars missile defense program capable of unleashing megajoule-class UV bursts. But in the 1990s, they were shelved. Too bulky, too unstable, too expensive. But today, with new materials, semiconductor-grade optics, and a radically different mission, they're back not to vaporize missiles, but to actually power the grid. Today on Valley of Depth, I'm joined by Connor Galloway and Alex Valys, the CEO and CTO of Xcimer Energy. They're betting on a forgotten Cold War laser to build what they believe is the fastest, most scalable path to commercial fusion power. Let's dig in. Before we dive into today's episode, a quick word about Payload Pro, our premium subscription for deep dive space industry insights, analysis on trends, and exclusive research you won't find anywhere else. Each week, we go beyond the headlines with original reporting, investor perspectives, and detailed financial models. Recent topics include SpaceX's projected 2025 financials, Kuiper's business economics, and the resurgence of satellite manufacturing. We also just published our first report, The Case for Space, a 50-page investor's guide to the space economy. If you're in the business of space or just want to understand it like an insider, subscribe now at pro.payloadspace.com. That's pro.payloadspace.com. Alex, Connor, thanks for joining us.
Thank you, Mo.
Happy to be here.
Let me start with a pretty important question. Is fusion energy having a moment right now? Like, what do you think has changed in the last couple of years?
Well, I think it's undeniable that fusion energy is having a moment, and there's a few different factors for it. The most recent one was the ignition shot on the National Ignition Facility at Lawrence Livermore in December of 2022, which made NIF and laser inertial fusion the only fusion concept to experimentally exceed break-even. But I think the moment, so to speak, actually started before that. And I think the transition largely came from investors' attitudes about deep tech efforts. Back in the early 2010s, obviously there's a lot of venture activity, but it was mostly focused on software startups. And I think the success of companies like Tesla and SpaceX, not to give all the credit to Elon, but he deserves quite a bit of it. I think it led investors to sort of change their perspective on what was possible in privately funded deep tech efforts. And I think that was the beginning of what started to change investor attitudes towards fusion. And that transition is in large part what led to the moment we're in today.
And we'll talk a little bit more specifically about NIF and laser-based fusion, and of course Xcimer as well. But I do want to ask, how close are we to commercial fusion? And do you think that the perception of fusion versus like the scientific and technical realities of where we are today fit with each other or aligned?
I think the perception in many ways is misaligned with the reality. I think many people's perception of the state of fusion is still decades out of date. And, the old sort of joke about fusion is perpetually 30 years away is still what a lot of people that are not paying close attention to the field think of. So it's misaligned in that way. With respect to how close we are, I think I'll let Connor touch on what our perspective is on that.
Yeah, I think there's a high likelihood that there's at least one company, probably a few, that can deliver electrons to the grid in the next decade. Now, that means somewhere between 2030 and 2040. I think we know what it takes to heat a plasma and achieve a burning plasma configuration, especially in inertial fusion. Tokamaks are really close. The jet tokamak almost got to scientific break-even. And now the field has strong investor support and interest from financiers. But there's a lot of hard engineering and scaling to do to build these machines. Fusion's not a tabletop. It's not tabletop system. Tokamaks and inertial fusion systems are large, and there's a lot of supply chain challenges in building out components. But we know what it takes, and so that kind of puts it on decade time frame. I'm fairly confident that in that 10-year window, there's going to be electrons on the grid.
Yeah. Okay. Well, let's talk a little bit about you guys. So you met at MIT about 20 years ago, more than 20 years ago. I don't want to put an age on you guys. It's just my estimates. What was the first conversation about fusion that you guys had that really kind of told you that Xcimer is a company you want to be building? Tell us a little bit about the founding story.
Yeah, well, our interest in fusion goes way before Xcimer. Right? We founded Xcimer in 2022, but we were roommates at MIT undergrad in 2004. So yes, that you can infer our age from that. So I went through the Plasma Science and Fusion Center at MIT. So I was, of course, very interested in fusion. To me, and Alex may remember a few other conversations, but some early conversations I had around fusion was around the Orion pulse nuclear propulsion concept. That's one of the things that got me interested in fusion. Actually, it wasn't energy production; it was space propulsion. I was a Star Trek nerd growing up, so some early discussions around that, and of course, that involved inertial fusion systems to power that. And then, not too far after that, our time in Los Alamos, learning about the Halite Centurion experiments, which we could chat a little bit more about. But in the 1980s, the nuclear weapons labs successfully ignited laboratory-scale fuel capsules. And it worked inertial fusion worked in the 1980s, and very few people are aware of that. And that got us very excited about laser inertial fusion.
Can we, Connor, could you just for the benefit of the audience, let's just take a quick step back. Tell us the difference between some of the more, common types of fusion energy or common approaches that companies are using. So like magnetic fusion versus inertial fusion versus there are some hybrid approaches. Just give us a little high level of what the differences are between them.
Yeah. So, at a high level, to make fusion happen, you need two things. You need to heat the hydrogen plasma up to several kilovolts, tens of millions of degrees. And but that's not enough to get a bootstrap heated plasma. You need confinement. So you have to heat up enough plasma. And it's that heating up enough plasma that's the huge challenge. And so there are generally two methods of confining the plasma that are pursued here on Earth. Of course, there's a third, which is gravitational confinement, and the stars do that, but we're not doing that here on Earth. One is inertial fusion, which was actually the first to be demonstrated. I mean, nuclear weapons operate on the principle of inertially confined plasmas. And the idea there is you very, very rapidly heat fusion plasma and compress it, and you get the fusion reaction rate so high that you get a significant burn of the fuel before it has time to expand and disassemble. So it's typically very high density, very short confinement time, but the product is enough to exceed the Lawson criterion. The far other end of the spectrum is magnetic fusion, which you very, very long confinement time and low density. But the way you can't confine it by its own inertia, otherwise it'll be gone before you can make power. So you use magnetic fields to trap charged particles. And generally, if anyone studied electromagnetism, charged particles are confined to field lines. And so the general idea of magnetic fusion is you apply a strong field to keep the plasma confined long enough to get power out of it.
So coming back to Xcimer, so was NIF really the sort of catalyst for both of you to go and start Xcimer?
I would say catalyst is probably correct. We, had learned about all these technologies that we're now integrating at Xcimer, in our time at Los Alamos, and Connor really spent a lot of time, even before that NIF ignition shot, basically iterating on the best approach with, our network of people in the field. And I don't think we really had an idea of what form it was going to take to actually implement the concept that was coming together. The initial discussions were just about, hey, what are the best technologies that we can take from all of the concepts and things that have been proposed over decades at the national labs and before. It was not the NIF ignition shot in December of 2022. It was a shot in August of 2021 when NIF got a gain of about 0.6. Outside of the fusion community, no one really cared. It was another sort of inscrutable intermediate result in a particular variety of fusion, and no one really noticed. But inside the inertial fusion community, everyone said, "Oh my God, NIF worked," and it was pretty obvious to everyone in the field that NIF was, just a fixed amount of time away from actually achieving gain greater than 1. And so it was that shot in August of 2021 that actually made us say, okay, this is probably the right time to put these ideas into motion. And it was also many of the people that we were talking to in the fusion community that said, hey, you have a really good idea here, and you should go do this. Now's the time. So we actually started Xcimer and pulled together, the official mechanism and infrastructure for the company about 9 months before the NIF shot in December of 2022.
Yeah, it was that shot. If you had to pick one point, it was that gain 0.6 or 0.7. I can't remember exactly which one, but ahead of the actual break even, where an ignited plasma was produced. That was okay. Let's go. But it was a culmination of many years, many nights and weekends, working out of the bedroom. Working another job to pay the bills, doing calculations, iterating on pitch decks, engaging with fusion experts in the field, getting feedback. Okay, yeah, that's going to be a challenge. We need a story for that. And just, working over several years to arrive at the integrated picture that is now Xcimer.
And this was during the pandemic also. So I think the other thing that stands out in my mind was, just how sort of incremental the whole process felt like. We're both working out of, our homes in California in sort of isolation and sort of gradually pulling this story together. And it probably didn't even feel as real as early as it does in other startups where, you have a defined transition of like, okay, now you have an office, et cetera.
But the seed goes all the way back to our time at Los Alamos and those halide Centurion experiments I mentioned. Back then we were convinced that if you can build a 10 megajoule laser, you can get the commercially relevant gains. So we knew that any future story was going to be centered around that. We just had no idea that we would be here today with the progress we've made.
So talk to me about I know you've raised $100 million. What were the early conversations like with investors? And how hard was it to convince investors to take what you guys were doing seriously?
It was a lot of conversations, both with investors and experts in the field, all at the same time, building credibility, discussing what we were doing. One common question, a theme about our technology is we build on a lot of innovations from the Strategic Defense Initiative in the 1980s, where Xcimer lasers were pursued for missile defense applications. And, there's kind of a unique picture is how the pieces were put together, but it was overlooked by scientists back then. And a common question is, well, if you can build a cheap laser, why didn't the government do it? That was a common question. Well, why isn't it here? And it's like, well, these are huge programs. The government moves slow. There's a lot of politics in the government. There was a lot of competition between Livermore and Los Alamos during the Cold War. There's a long history there, and it's kind of hard to explain and get through. So that was one question we commonly got. Well, why wasn't it done before?
Right. Well, okay. So let's. I want to go back to NIF for a second. So, you guys both referenced this August 2021 first experiment, and I believe it was like 70% of the laser energy was converted to fusion, and the output was something like 1.3 megajoules. Since then, the output has, they've tried multiple shots. They continue to increase the energy output. What is NIF's goal right now? It's because they got to the first break-even point, and they're now continuously increasing the energy output. But from my understanding, this is not a facility. It's a government research facility that was built to prove ignition physics. But can it produce electricity? Can you tell us a little bit? Can it produce electricity? Can it run at high repetition rates?
No, it cannot. So first, the NIF was built not for fusion energy. It was built to demonstrate ignition, but it was funded for national security applications and United States stockpile stewardship. So it was never meant to achieve commercially, very high gains or high rep rate. And they've done a phenomenal job getting to where they did with 2 megajoules, which in our view is limited laser energy. So they've gotten 8.6 megajoule fusion bursts. They're working to get an upgrade to the system in laser energy to get to 2.6 to 3 megajoules, to see if you can get 10 to 20 megajoule fusion bursts. But that's probably as high as they're going to get on the facility. But that's useful to do some national security projects. The NIF is not commercializable technology. That's the challenge for taking what they've demonstrated on the laser side and commercializing it. The laser was several $1 billion, very expensive, and 0.5% efficient. But most significantly is optics damage. So there's a major optics refurbishment program. They do about 400 shots per year there, and they have to spend $40 million a year to replace optics, because even to get to 2 megajoules, they're really pushing damage thresholds. And so every time they shoot, they damage glass, and they have to inspect every beam line and look where the glass has been damaged, take out the optics, and refurbish. That's not a commercially viable system. So you need higher efficiency, and diodes are promising to do that if you pump it with diodes, but the cost of diodes is extremely high. And then you can't scale any solid-state architecture affordably to much higher energy than the NIF because of this optics damage problem. So there's not a path to a 10 megajoule laser based on a NIF technology, and certainly not a path to a 10 megajoule laser that can fire it can be affordable and also fire one shot every few seconds, which is what we're doing. So to commercialize the NIF success, we are completely rethinking the laser, but we're shooting the same type of fusion fuel capsule, just at much bigger scale.
And that's the DT fuel capsule?
Yes, the DT fuel capsule has a plastic ablator, and then the deuterium, tritium fuel inside, and it's spherical, and the ablator absorbs electromagnetic radiation, blows off, and that creates a reactive force that compresses the DT fuel inward. When that fuel stagnates, it gets hot and dense enough to have a self-sustained burn wave and burn a large fraction of the fuel before it disassembles. So that's the mechanism that worked on the NIF. That's exactly the same mechanism that we are pursuing at Xcimer.
I think it's worth pointing out for the NIF that despite the enormous success in the milestone that their result is for the fusion community, NIF gets essentially zero funding for the purposes of fusion energy. And as Connor said, the facility was funded and their current operations are funded essentially entirely for national security research and stockpile stewardship. And the benefit to humanity of fusion energy and ignition is sort of a side benefit of that. And one other consequence is that they actually don't have that many shots on the NIF machine that they can actually use to try to push the boundary of ignition. A lot of experimental time on NIF is used for other purposes. So the progress that they've made since December in going from 3.6 megajoules to 8.6 megajoules is even more impressive in that sense, in that they actually haven't been working continuously on it in terms of iteratively improving on the machine. But it's also important for people to understand essentially all of their funding is directed towards other applications.
So, Connor, you mentioned a little bit about sort of like, well, why hasn't the government done this before? Let me ask it slightly differently, which is, why hasn't this been done before in the private sector?
Yeah, it's a good question. So one aspect is the large dollar entry, right? These are $1 billion programs, either a tokamak or laser fusion of order, right? For these very well proven scientific approaches, but also the programs in the 1980s that we're building on were highly compartmentalized during the Cold War. Like all the laser weapon defense work DoD funded was very compartmentalized from the work going on the fusion side. There wasn't much crosstalk, so you really have to dig in and do a lot of archaeology to put the pieces together to, wow, if these people talk to these people, this could have happened 20 years ago, like if there was this communication. So I think it's, just spending a lot of time over the years, talking to experts and doing that archaeology and putting the pieces together. And there just hasn't been investor interest in other than very rare companies in funding multi-billion-dollar programs to electrons on the grid until recently. And no one's really done that archaeology except for us.
I want to also emphasize, aside from the point I made at the beginning about, investor interest in capital-intensive, long-term, deep tech projects is fairly new. But the other factor here is that this is just a very, very small field and a small community of people. And so, often when we talk to investors that are used to investing in much more sort of widely known fields, in other fields like drug discovery, for instance, right? Like there's just many more research groups from all over the world that are constantly thinking about and like monitoring the state of the art and competing, right, to see who can improve things. And the origin of fusion, in particular this kind of fusion, of laser-driven inertial fusion from the U.S. National Security Complex, it just means that the group of people that spend their days thinking about this is incredibly, incredibly small. And so the answer to a lot of these questions of like, why didn't someone else do this before, is just, there was no one who was in the right moment to actually make it happen.
So what kind of progress have you guys made so far?
Yeah, so we raised our Series A financing, and the first major step on our roadmap that capital allows us to do is build a prototype laser system we call Phoenix. Here in our facility in Denver, we have about 70,000 square feet of laboratory space and 12,000 square feet of office space here. And our specific approach to a scalable architecture is using a gas laser. It's called an Xcimer laser, in particular krypton and fluorine. And these lasers can scale to much higher energy affordably than solid state lasers in terms of dollar per joule. The snag is they're cheap and efficient at long pulse lengths, long being a quarter of a microsecond. Fusion needs nanoseconds. And so you have to somehow take the pulses from these low cost and scalable gas lasers and take that laser pulse and compress that energy and time down to the nanoseconds you need. So there's a process called stimulated Brillouin scattering. It's well known in physics and nonlinear optics textbooks, but it's probably not widely known to the general layman. But it's a process by which you can do energy redirection and compression all in a gas. And gases can handle much higher energy densities than solid optics can. So you can have a beamline be much more compact and get rid of a lot of the optics. So those two pieces are key to getting to a 10 megajoule driver. It's using these gas Xcimer lasers at a microsecond and longer, and then using what we call gas optics, this SPS process, stimulated Brillouin scattering, to both reflect and compress laser pulses so you can get them to a target in the nanosecond duration. So what we're doing here in Phoenix is we're working on both aspects. Our first DOE technical milestone, was completing what we call the long pulse kinetics KRF laser. And that's the first laser ever built to operate over a microsecond in KRF gas. So really benchmarking our codes and modeling for building these e-beam pumped KRF lasers at long pulse length. And the other key thing that we're built at a part of Phoenix is a demonstration of this SPS gas optic technology. So in Phoenix, we'll increase the TRL of both of those to a high enough level that we're ready to execute our break-even machine project, which comes next.
Got it. Okay, so Phoenix is not going to is not the technology that gets you to break even.
It's the technology, but not the system. So it's demonstrating the technology, but it's not the machine. It's not the laser system that's going to achieve break even. And that's our next bigger machine.
Got it. Okay, and what's sort of the roadmap for the next bigger machine?
Yeah, so the next bigger machine will involve many what we call Argos laser modules that are bigger than what we're building here. So when we execute the program for our break-even machine, we'll build a prototype Argos module and mass produce them. And the break-even machine will have 30 to 50 of these modules, of these KRF laser modules that are, and their laser beam output will all be compressed with this gas optics process I mentioned and delivered to a target in a new facility that's separate from the one here, where we will achieve engineering break-even.
And is this the Vulcan?
Yes, this is Vulcan, and our Vulcan break-even machine. And so the plan for Vulcan is we believe we can get engineering break-even with a 4 megajoule direct drive illumination geometry. And so what that means is the fusion energy burst is over twice the energy the laser took off the grid electrically. So that's the goal for Vulcan. And our plan is to build Vulcan and have it be directly scalable up to over 10 megajoules in place. So this will be a very high energy laser facility, but there won't be a fusion blanket. It'll just be a single shot demonstration of this engineering gain, break even. And also, of course, an asset for national security applications, because it'll be like NIF, but much higher performance. And then the third phase is where we build a fusion pilot plant. So that's after we call that Athena.
Athena. How did you guys come up with the names?
Alex?
That's one of the hardest things in all these programs. We started with really bold ambitions that we were going to be more creative and not use Greek and Roman gods. And then you discover, when you have other things, people can't spell them, or people don't know what they mean, or you come up with a cool name and it turns out to be like the god of despair in, some other belief system. So we had a contest actually inside Xcimer to settle on the names, and then we pretty much ended up just choosing the same system that people use elsewhere. Unfortunately, there are some laser systems in the UK that were named Vulcan and a few other overlaps, but
Yep, no, it makes sense.
Ultimately, we decided to pick some names and then get on with the work.
So I want to talk about some traditional fusion reactors and this issue that they have, which is neutron damage. You have to replace the chamber walls every couple of years. Tell us, is this a problem that you're going to face? And if so, how are you dealing with it?
Yeah, that's a great question. I mean, that's one of the early things that we thought about is how do you come in with an integrated picture that is really viable on the back end, and got really excited when learning about the reactor concepts that use what's called thick liquid wall protection. So yes, most reactor concepts and tokamaks have a dry wall. That means you have steel or some material that is exposed to the fusion plasma. It's called a plasma-facing component. And that material gets hit by high-energy ions, X-ray radiation from the brimstone from the plasma, and 14 MeV neutrons. And so most tokamak systems envision having to replace the first wall over some period, and there's still not any system in existence that can qualify materials for what first wall should be made out of. There's no system that can accumulate the displacements per atom or the DPA needed to qualify and test materials. So there's a lot of discussion in the field around who's going to build the first prototypic fusion neutron source to do this qualification. So it's a common topic. Livermore, actually, back in the late 70s, as part of the weapons program, the very first concept that the National Lab Weapons Complex put forward for how you make power from inertial fusion solved this problem in the late 70s. And it was, if you can have your coolant, either flied molten salt or lithium metal or some coolant. And the first design was lithium, later design was flied, which is the same material Commonwealth Fusion Systems plans to use. But if you have this in a waterfall and you're somehow able to inject the target and get the beams to the target inside the flow and have your steel be behind this waterfall, then your coolant acts as a shield. So it's thick liquid wall protection. And this concept was called High Life. It came out of Livermore and Berkeley, a lot of tremendous work in the late 70s, 80s, and 90s. High Life stands for high yield lithium injection fusion energy. And this protects the steel. So the main advantage of being able to use liquid walls, thick liquid walls, is it blocks all the X-rays, all the debris, and those high-energy neutrons are moderated down to a spectrum like what you would see in a fission reactor. So we can use steels already qualified in fission reactors for our first wall. We bypass the need for a prototypic fusion neutron source. We bypass the need to replace the whole first wall. So it's a major advantage. And really only inertial fusion has this. You need, and also in particular, our approach. So one thing that drove our laser architecture was this. We want to use thick liquid wall. Well, that puts two constraints on how you engage the target with a laser. One, you need to go to low rep rate. So you need to be shooting under 1 hertz or once every few seconds, because when the fusion burst happens, you vaporize a few kilograms of the coolant, of the molten salt, and that vents and you get droplets and spray, and that has to take some time to recondense and the droplets to fall into the pool below. And it's about 1 hertz is the threshold. If you're much faster than 1 hertz, there's not enough time for the chamber to clear to propagate beams again. So it makes it infeasible. But if you go to low rep rate, there's no issue with chamber clearing there. The other issue is if you have hundreds of beams coming in, NIF has 192, how do you erect liquid jet flows through hundreds of beams to protect the first wall behind the beam ports? It's also a challenge. So that's what drove us to just 2-beam illumination from very small penetrations. So we really have the real estate to erect these flied flows. So that really drove the laser architecture as well, as bringing in energy from a small solid angle and operating with very high pulse energy, high yield, and low rep rate. And that's a major advantage of our approach.
Got it. In terms of getting to engineering break even, can you share a little bit about how much total capital you expect to need?
Yeah, so I'll just say it's a billion plus project.
Got it. Okay.
That's where I'll leave it for now.
And where you stand right now, what's the biggest unknown you're still solving at the physics level?
So the biggest unknown, I would say, is this gas optic operation, and that's why Phoenix. Why the primary deliverable for our Series A is demonstrating this SPS gas optic operation, and that we can implement this process where you can reflect laser energy, compress it in time, and we also need to do it with pristine beam quality, so that the short pulse output from this process that will engage the target is very good beam quality, so we can drive the target uniformly. So demonstrating that process, that the gas optic physics works as expected at significant scale, and we can do it with what's called diffraction limited beam quality. That's the next major de-risking that Phoenix will do.
I think it's worth pointing out that very few of the things that we're looking at for this system are physics unknowns in the conventional fusion sense. The fact that we're leveraging the successful demonstration on NIF and then the earlier work at Halide Centurion is part of the reason for that. There is no fundamental unknown about is it feasible to generate high gain from inertial fusion. A lot of the stuff that Connor's talking about is essentially, a hybrid of engineering and cost unknowns coupled with science. Like we know what we need to do from a scientific perspective to make the process work. The question is, can we build a system that we can deliver on our schedule within our cost targets that actually achieves those requirements?
Yeah, and that's because we're the only company directly scaling what worked on NIF to commercial operation. And by what worked on NIF, to be very clear, what I mean by that is you have a spherical fuel capsule and an ablator, and it's heated by electromagnetic radiation, blows off, and you get an implosion, and it ignites and burns. We're the only company that's scaling that to much bigger size. And in inertial fusion systems, the gain is a significantly sharp function. When you're right at ignition threshold, the gain is a sharp function of energy. So by going to 30 times the fuel mass, 30 times a bigger massive target, we'll be above the yield cliff and up in the robust burn regime, where gains 150, 200 are very feasible. And the Halide Centurion program de-risked this too. So it's for us, it's all about the laser. Can we build this laser affordably, cheaply, with good enough beam quality and get the energy to the fuel capsule? If we can, we know high gain is achievable.
How do you, well, let's talk about your customer base for a second, because we talk about NIF and like NIF's heritage. Are your first customers grid scale power? Is it defense infrastructure? Is it something else?
Yeah, so there's two different sides to that question. I'll take the sort of obvious one first. Our goal ultimately with Xcimer is to produce grid scale baseload power plants. And at the moment, we're leaving our options open in terms of, what is the most likely commercial manifestation of that. Because you can imagine a whole spectrum of outcomes, including Xcimer, building and operating power plants and directly selling electricity. I think the most likely outcome for the commercial deployment of Xcimer technology is very similar to what happened in fission, in that Xcimer will build the fusion cores of power plants, the laser, the fusion chamber, the fuel processing systems, and things like that, and then sell those to power plant operators that will actually do the work of the licensing and permitting and specific, regional considerations wherever you're actually building the plants. And then, of course, the revenue model, in addition to selling the hardware, is selling maintenance, and servicing and things like that over the life of the facility. As I said, we're leaving our options open. Other things are possible, but that's sort of the default that you get led to when you think about what does the business look like here. The other part of your question, though, in terms of who is our actual first customer, it is quite likely that the first customer for Xcimer will be someone using our lasers for another purpose. And the origin of these laser systems.
I can only guess who that someone might be.
Who that customer might be, right? Well, same here. But the origin of these systems in the Star Wars missile defense programs and other directed energy applications means, especially today, as I'm sure you know, all this stuff is becoming much more topical with Golden Dome and other things happening around the world, and so we are actively pursuing applications now of other places where these very same large excimer lasers could be used for defense related applications. And so, that would be great. It'd be, our core mission will remain fusion energy, but fusion is very expensive, as we just discussed, and there's a very real opportunity for us to contribute in other ways and bring in some revenue to fund the fusion mission.
How do you think about the cost of energy per megawatt hour? Like, what numbers do you think? I mean, it's easy to talk about sort of the fuel density and the amount of 1 gram of fuel equal to how many tons of coal or typical hydrocarbons. Like, talk to us about how you're thinking about the cost per megawatt hour, and how do you become competitive?
Yeah, so from the beginning, Connor and I knew that we only wanted to do this if there was a path to be commercially viable in the end. The technology is really cool, right? And the science is cool, and the systems are cool, but we're not doing this for research purposes. We're doing this for commercial applications. And one of the things that got, I think, both of us very excited about inertial fusion when we first learned about it is that inertial fusion has very good prospects for good economics because the systems are so decoupled. Unlike some magnetic confinement systems where you have a lot of very exotic technologies that have to be packaged in a very complex, very tight and harsh environment, inertial fusion systems are much simpler. The chamber is just a large vacuum vessel. The fuel capsules can be manufactured and fueled off-site or sort of independently of the chamber. The laser, of course, is physically decoupled. And so in the long run, there's a path to really drive down the manufacturing cost of all these systems when you're producing them in volume. So our target, which we've had since the beginning, is we want to get to levelized costs of electricity for nth-of-a-kind plants of $50 per megawatt hour. And that is very competitive with every other source of energy, fossil fuels, of course, but also renewables plus batteries. And I think particularly if you look at the economics of baseload plants and what it's going to take to support electrical demand of 2 times or 3 times our current baseload in the 2030s, that is a very competitive number, and it looks very achievable for us for nth-of-a-kind plants. We're not saying that the first pilot plant we build is going to deliver that cost, but when you're building them in volume, it's quite achievable.
How much of your supply chain are you verticalizing?
Also a great question. We're being very strategic about where we invest our efforts in bringing production in-house. There's probably very few other industries that have the same breadth of technologies and components and sort of vendors and suppliers that you would need for something like a fusion power plant. And I think the best way to answer how we're thinking of it is there are some parts of the supply chain that are not really used to operating in a commercial environment. And those are the ones that probably bring the most benefit for us to bring in-house by reducing costs and just improving efficiency of some particular area that's been supplying components to academic research for the past 30 years. There's other parts of the supply chain that are very well established and that have been working in a commercial mode for decades already, where there's less benefit to us or less potential improvement in bringing it in-house. So there's no single answer, but we do expect that ultimately, when Xcimer has demonstrated break even and built the first pilot plant, the business that we're going to be in is getting very good at manufacturing the fusion cores of power plants at low cost, and that will be a pretty integrated supply chain.
So I want to take a quick detour, just one quick detour question around sort of the national security use cases of an Xcimer Energy, Xcimer laser, excuse me. And this is a theoretical question. I'm certainly not suggesting anyone is buying the laser for this, but could your laser be used to vaporize a missile?
Yes, that's not so
Okay.
theoretical.
Okay. So maybe walk me through like how power, for someone trying to like, I mean, we're throwing out like these terms, right? Megajoules, like help us understand like how powerful this laser, like what could it do?
Yeah. So just to be clear, it's not going to vaporize the whole missile. But damage it, shock it where it fails. Right. That's the goal for directed energy systems. So, I can't talk about specific numbers here, but I can give you a general idea of what the concepts were in the 1980s, out of which this technology was born. The idea is to have long range and get high fluence in a few microsecond pulse on a structure. Fluence is energy per area, so joules per square centimeter. And if you have a high enough fluence, even in a very fast pulse of a few microseconds, when your beam hits some structure, it'll heat it and ablate it. Very similar to how you drive a fusion target. You heat, ablate, it blows off, it launches shocks in, you can compress fuel. Now, ablating the plastic ablator on a fusion target is way higher intensity than any directed energy. You can't propagate that high intensity through air. That's why there's a vacuum chamber as the laser's coming into the target. But still, even in the atmosphere of space, if you have high enough fluence, you'll ablate off some structure that'll launch a shock into the structure, and that can cause failures. So that's the mechanism. And I can't talk about specific numbers, but yeah.
Do we think Superman's eyes potentially are excimer lasers? If you've seen the movie recently.
No, I haven't seen the movie, but I'm guessing you can see the lasers coming out of his eyes, and excimer lasers are typically UV, so you can't see them.
There you go.
Then though excimer lasers can fluoresce the air at high enough intensity, so. Anyway, but probably not. Wrong wavelength.
I appreciate you entertaining my question. So let's talk about the fusion landscape. There's probably 30 to 40 plus fusion companies out there right now. What are some approaches that you admire and others that maybe you think are more challenged?
Yeah. So the way I like to answer this question, instead of talking about any specific fusion company, I can talk generally about fusion approach, and I think it's really well summed up in what's called the Lawson parameter, which is density times confinement time, and that's often plotted versus temperature. And there's some great papers by Sam Wurtzel and Scott Shue. They've recently updated a paper that has just great plots of accumulating data from across the whole world about different experiments of all different kinds: stellarator, tokamak, inertial, magnetic liner fusion, Z-pinch, of where systems to date, in terms of where's the best performing system of this approach in the world, and what Lawson parameter has it achieved, and what temperature. So there's a few different plots related to the Lawson parameter in the paper, and you want to look to the upper right. What's the best performing systems in terms of the core plasma physics? And if you go to the upper right and you look, you'll find laser inertial fusion is the best. It's achieved ignition. It's achieved fully ignited plasma. It's surpassed ignition, the Lawson parameter needed for that. And if you look down a little bit, the next best performing systems are tokamaks. The jet tokamak almost achieved scientific break even. Stellarators are similar. Walk down some more. There's magnetic liner. And you keep walking down, and there's other approaches. So the way to answer that question is, as a fusion investor, you can have a philosophy of, before I answer that question, if you walk all the way down, there's some approaches that are very far from break even, but if they work, they would be very low cost and compact and small. And you could take the investment philosophy, if I'm going to invest there, because if we win this gamble and we can make this huge jump in plasma performance, we'll beat tokamaks and lasers because we'll beat them on cost. Or we can deploy much smaller power plants. You don't, to get good economics, you don't need 100 megawatt plus, et cetera. But that's a big gap in Lawson parameter. Our view is you start where the plasma physics works, because you can spend billions and billions of dollars on the wrong approach where you're far from break even and just at the whims of nature. And if you don't get to the Lawson parameter you need, nothing else matters. So my view of where you want to look, of what approaches to keep an eye on, are just look at that plot. Where are the best performing systems? How can you commercialize those? And it's still worth looking at the others, but not betting big on them, in my view. So that's how I view it, and that's how I chose laser inertial fusion to work on out of all the different approaches.
So I've seen the chart that you're referencing, and I have to ask, like, there are companies that are on that chart that are far from the top right corner. What, like, just to play devil's advocate for a second, what causes someone what causes a founder or an engineer to go after one of the ideas that doesn't fit into the far right corner of that chart?
Well, it could be some new ideas that could move you a little bit along the way, and they just have conviction that maybe this can move us all the way. So, I mean, most of those ideas were all thought up in the Cold War days, like across the whole gambit of them. They're not new concepts. They came about 60s, 70s, 80s. Almost all of them were explored in some national lab at some level. I think you have other companies figuring out improvements, ways to improve what was done, and the hope that those improvements can take you a long way in loss and parameter space. But the challenge is plasma physics is tricky. It's turbulent. There's a lot of instabilities. It's not, it's a hard subject, and you can be on a path where you're making significant improvement, and then you hit some nonlinear threshold and you just stop and you never go past that. And like things like that have surprised multiple approaches as improvements going. So there's still a probability you can get there. So I think it's people thinking they can be innovative and clever, and maybe they can. I mean, I'm not saying people shouldn't. Like, there should be research in all of them. By far, there should be research in all the approaches. But in terms of what you're going to throw huge $1 billion at to commercialize, you want to look where the plasma physics works.
I'll elaborate on my own thoughts there. I think there's different things that motivate people. And obviously, there's probably some companies that are, sort of on the bottom half of that chart that have some insight, right, or some edge that they believe means that that approach is more promising than the experimental results to date would indicate. And I can't claim to know what that is, but obviously, like, that's a possible motivation. I think another thing that, we should be frank talking about here in the fusion industry is, there are people, and society needs more of these people, that are just interested in doing research and are interested in doing, cool science and cool work to, move the field forward and produce results, and aren't necessarily themselves personally motivated by or necessarily need to believe that there's a 100% chance, right, that at the end of that, you're going to have a commercially viable system. And there probably are some companies, and I literally, do not have any in mind when I say this, but there probably are some companies where there's a little bit of a mismatch between the intent of, the team that's working on it and the expectations of the investors. Just saying, if you look at the space of 65 fusion companies, it's pretty clear that not all of them are pursuing things that are robustly going to work in a commercial sense.
Yeah, I agree with that. I want to talk about the future. What keeps you going, right, when the odds are long and the funding rounds in particular are hard?
Obsession. That's the answer. Just an extreme obsessed personality. Kind of a mentality like just never give up. Just going to keep going, keep trying. So a desire to change civilization, a desire to do cool science, though we're not just doing this for cool science, as Alex mentioned, but it's part of it, a desire to have an impact to the planet. For me, getting into space is huge. As I mentioned earlier, I was a Star Trek nerd, and I went to MIT thinking I'd figure out warp drive, and boy, was I humbled after taking general relativity and QFT. But still, fusion to me is the what will get humanity into space, into the stars, and any advanced civilization going through technology will end up mastering fusion, and there's nothing past that. There's no more energy dense mechanism of generating power for any civilization until you get to black hole engineering, which is so far sci-fi it's not even worth talking about, right? So any civilization that goes to other planets, goes to other stars, will be powered by fusion. And so to me, it's like, wow, I want to be a part of that. So I think that obsession is what drives me.
In terms of the potential effect on the trajectory of human future, there's nothing more fundamental you could work on or more impactful than fusion.
When is the first commercial fusion plant going to go live? When? Let me ask you differently. When is the first Xcimer fusion plant going live?
The fusion pilot plant, so mid 2030s is our goal. And to answer your question, as I said at the beginning, I think somewhere between 2030 and 2040, there will be electrons on the grid from a fusion approach. Just keep that general statement at a high level. I think that's.
Yeah. So then let's just say 2030 to 2040. By 2050, what does the world look like?
Good question. I don't know, hundred thousands of plants deployed potentially, but it's hard to say how long it would take. Maybe not that much different than today, given it's just a decade of real deployment. The question is, what does it look like in 2100 when full industries can then be massively expanded because you have a lot of power? Like, one thing we like about fusion is that you can generate as much power as you want without feeling guilty about it. And you essentially manufacture power or manufacture energy instead of drilling for it. So when the world moves to fusion, it's going to enable a massive step up and industry, AI, industrial processes. Like the world could look very different in 2100. But 2050, it might be, take a little bit more time. Anyway, Alex, what do you think?
Yeah, I mean, that gets to the answer of why I'm working on fusion. Humanity has not been thinking in terms of what are the limits of what's possible for 50 years. For 50 years, we've been aware that fossil fuels and sort of the driving force of human progress, energy, have huge externalities that, we care increasingly more about. And for the past 50 years, we've been thinking about efficiency and about conservation and, about how to minimize our energy use and minimize our impact. And all of that is great. But the potential for fusion is to sort of unleash us to think again about what's possible if we had unlimited energy. And I actually think it could happen faster than 2100. I think from 2040 to 2050 is when we will start to see new industries and new applications that are made possible only by essentially an unlimited source of energy. So I think we can change the world faster.
Yeah, but I guess I meant like the world's looking like the Star Wars home planet, right? Mass industry all around. Like some big change is going to take a bit longer.
Yeah, no. You look. I think it's interesting. Anytime you've had this massive exponential increase in energy density across different fuel types, which we've seen from fire to wood to hydrocarbons to fusion fuel in the future. Like it's impossible to say for sure what it's going to look like. But if history is any is any record, then you can totally expect there to be a really, really significant and massive change in the way we operate as a society. So anyway, Alex, Connor, thanks so much for being on the show. This is great. I mean, you guys have a lot of upcoming milestones coming up, so we're going to be following along very closely, and we hope to get you guys back on the show real soon. So thanks for taking the time.
Great. Thank you. Really appreciate it.
All right. Thank you, Mo.
Until next time.